Hello, friends. How are you? I hope you're having a wonderful, wonderful day. Again, Engagely sort of blinked out while it was recording our class today. So I'm just going to go ahead and redo this and kind of whiz through this. If you're watching the recording to take your notes, be sure to pause this as you need to. Okay, so today is the second day of the second week of our 5-week semester or for the summer. So it is July 1st. Crazy, crazy, right? Do take note that on Thursday, July 4th, before our holiday, our school holiday of July 4th, we are going to be taking our Unit 2 exam on motion and forces. Okay. So here you can see our Unit 2. We've talked about motion. We've talked about Newton's first law and forces. And then yesterday we talked about Newton's second law, F equals ma, or force equals mass times acceleration, and his third law, equal and opposite reactions. So today what we're going to do is we're going to talk about the kinematics of free fall, and we'll talk about momentum. Tomorrow we're going to include collisions and impulse, which is going to set us up for that exam before we leave for our 3-day weekend. So today we're going to talk about the differences between mass and weight. We'll describe the effect of gravity on objects, as well as define what free fall is. And then we'll calculate the velocity of an object in free fall from Earth, and then we will move from there over into momentum and explain how mass and velocity affect momentum. So make sure your notes are open and you have clicked OK on question number 1, just confirming that you understand that in the summer term, 100% of your grade is dependent on these notes and the exams that we complete in class. So let's brainstorm for just a minute and think about watching astronauts, right? When they are on the moon. Have you ever seen an astronaut when they're walking on the moon? It almost looks like they're jumping and they're like playing hopscotch on the moon, right? When they're just walking. And that's because it's much easier to jump. It takes just a little bit of force because the gravity on moon is pretty small. It's only 1.6 meters per second squared, which is really, really small in comparison to Mother Earth down here. I know also in outer space there is zero gravity, and that's why in outer space astronauts just sort of free float around, right? So gravity plays a large role in our lives. And one of the ways that gravity plays a role is it is the difference between mass and weight. Mass is the same everywhere. Doesn't matter if we're on Earth or the moon. If my mass is 56 kilograms, sorry, I was trying to say kilometers, that's crazy, kilograms, it is going to be 56 kilograms on the moon, and it's going to be 56 kilograms on Earth, because it is just a measurement of the stuff, the matter that I'm made up of. Mass has volume, right? And it's going to be the same everywhere. Now, weight is a little bit different. Weight incorporates the force due to gravity. So it changes based on the acceleration due to gravity. I know that the gravity here on Earth is 9.8 meters per second squared. Again, on Moon, it's 1.6 meters per second squared. And in space, there is 0 gravity, right? So you can see my weight, if my mass is 56 kilograms, my weight on Earth that takes into consideration the gravity of 9.8 meters per second squared, my weight is going to be 560 newtons. And you compare that to my weight on the Moon with 1.6 meters per second squared, my weight is only going to be 92.59 newtons. So much, much less, right? And what is my mass, or what is my weight? What is my weight in outer space? Well, if gravity is 0, then guess what? My weight is also 0. So kind of cool, they're a little factoid, right? So because I have more gravity on Earth, I'm going to weigh more on Earth, but I have the same mass. If I have less gravity on Moon, I'm going to weigh less, but I'm still going to have the same mass. And again, finally, in space with no gravity, I'm going to weigh nothing. Absolutely nothing. But I'm still going to have the same mass. So that brings me to this question right here. What is weight based on? Is it based only on mass? Is it based only on gravity? Or both mass and gravity? Or neither mass nor gravity? And if you chose both, then you would be correct, right? And that is the answer to question number 3. Okay. So question number 4 is complete on your own. Okay, complete on your own. Here we see we have 2 planets, planet A and planet B, and we have a single astronaut, and the astronaut has mass of 65 kilograms on planet A and a mass of 65 kilograms on planet B. However, their weight is very different. On planet A, they have a weight of 233.35 newtons, and on planet B, their weight is 576.55 newtons. So, which statement is correct? Do both planets have the same gravity? Does planet A have more gravity or planet B have more gravity? What do you think? If you are unsure, go back and refer to question number 2. Okay, so what happens if you drop a brick and a feather at the same time? Which one's going to hit the ground first and why? Okay, answer that question to yourself and then go and watch the video that is linked at the top of your notes. Okay, and be prepared. This is one of my favorite videos. It's pretty amazing. Okay, so what you just saw is free fall. Okay, now I know that if I drop a feather and a bowling ball, right? In the world with air, with friction, right? I have the force of gravity pulling both of these objects down. But I have an opposing force. I have both the normal force and I have air resistance. And air resistance is a type of friction that opposes the motion of being pulled down, okay? And this is going to cause the bowling ball to drop at a faster rate than the feather, right? We all know that. However, what's astounding is if you take this out and you remove the air, then you have an object in free fall. And that's when they are only affected by the force due to gravity. And if it's on Earth, all objects have the same amount of gravity acting on them. All of them have a negative 9.8 meters per second squared, pulling them down towards Earth. And so they are all going to accelerate at the exact same time. So it doesn't matter if it's 1,000 kilogram mass or a 1 kilogram mass. It doesn't matter if they are round and shiny and smooth or if they have little wispy parts. They are going to all hit the ground at the exact same time because there's no opposing force to gravity. And that is what free fall is. Okay, so question number 5. Question number 5 is they all fall to the ground, fall towards Earth at the exact same rate. This was, I want to say one thing before we go any further. Okay, remember that gravity is the force which the planet Earth or some other object is drawing, is attracting towards itself, right? And the force of gravity keeps all planets in orbit around the sun. And this constant is a magnitude and is always, always positive. However, when we talk about acceleration, which is a vector, and remember that vectors have both magnitude, right, and direction. Only when we're talking about gravity as an acceleration vector will it have this negative sign to it. Otherwise, gravity is always positive. Okay, so just kind of a side note in your pocket. And that's why yesterday, when we were talking about the force of an elevator as it was falling, and we used the positive 9.8 meters per second squared. That's because, again, we were talking about the force of gravity that Earth was pulling on us, right? We weren't talking to the acceleration of gravity. We were talking about the force of Earth's gravity. Okay, so with that in respect, what is the acceleration due to Earth's gravity? Again, what is acceleration due to Earth's gravity on a 20 kilogram ball? Well, lo and behold, that's a negative 9.8. What is the acceleration due to Earth's gravity on a 200 kilogram ball? Lo and behold, same thing, negative 9.8. And that means they are going to have the same acceleration or rate of speed, and they are in free fall with no air resistance. Which one is going to hit the ground first? Well, we know that they are going to hit the ground at the exact same time. And this is question 6, 7, and 8 in your notes. Go ahead and pause and complete your notes as needed. Okay, so here we have our formula to calculate acceleration. Acceleration is equal to final velocity minus initial velocity divided by time. Now I can use algebra, and I can take this equation and manipulate my variables so that I solve it for final velocity. You don't need to know the algebra behind that. Just know that this is the equation that we are going to use to calculate final velocity due to gravity. Okay, so here I have a word problem. It says, what is the final velocity of an apple that starts at rest and then free falls on Earth for 4.2 seconds? Notice that it said that this is happening on Earth. So I know that the acceleration due to gravity on Earth is a negative 9.8 meters per second squared. So again, as I read this, it says, what is the final velocity? So this is what I need to calculate. Of an apple that starts at rest, that is my initial velocity. And if it's at rest, that means that is 0 meters per second squared. And it's going to free fall for a time period of 4.2 seconds. So this is all of my variables that I need. Notice that I am solving for final velocity. My initial velocity, I said, was 0 meters per second squared. Acceleration due to gravity on Earth is a negative 9.8. That's per second squared, times my time, which is 4.2 seconds, right? Now, next, what I'm going to do is remember my order of PEMDAS, right? Order of operations. It says I always have to do what's in parentheses first. So I'm just going to bring down my initial velocity of 0, and then I'm going to calculate negative 9.8 times 4.2, and I'm going to get a negative 41.16. Final thing I'm going to do is I'm going to add these two together, and my final velocity is a negative 41.16. So again, question number 9. Question number 9. Pause the video, fill in those boxes, and then start the recording back when you are ready. Okay, this one we are going to annotate together, but then you are going to finish on your own, right? So what is the final velocity? This is my final velocity that I need to calculate. Of an egg that starts at rest. Remember, if it's starting at rest, that means that is 0 meters per second squared for my initial velocity. And then it free falls on Earth, for the time period of 2.7 seconds. So here is my formula. My final velocity is equal to my initial velocity, which we said was 0 meters per second squared, plus gravity on Earth, which we said was a negative 9.8 meters per second squared, times time, and our time is 2.7 seconds. So with this calculation, right? Remember, you need to do what is in your parentheses, right? So you're going to multiply these two numbers and write it right here. Then you're just going to bring down your initial velocity right here. And then you're going to add them together to get the final velocity and the answer to question number 10. Go ahead and hit pause while you do those calculations. Okay? Okay, so moving on from free fall to momentum. Okay? Not that I want to, but if you had to be hit by a baseball? Would you rather be hit by a baseball going 100 miles per hour or a baseball going 1 mile per hour? I don't know about you, but I'm pretty sure that I would rather be hit with a baseball going at a slower speed because it's going to hurt less. Okay. Again, not that anybody wants to, but if you had to be hit by a vehicle, would you rather be hit by a semi-truck going 2 miles per hour or a car going 2 miles per hour? Well, again, I don't know about you, but I would rather be hit by a car going 2 miles an hour than a semi, because the semi has so much mass going behind it and it would just obliterate me and it would not be a good sight, right? Okay, so what we're talking about is momentum. Momentum is defined as mass in motion. And in order to change a moving object's motion, you have to overcome its momentum. So question number 11 is to change, right? Okay, now notice that the more mass an object has, the more difficult it is to change its motion. So it's going to have more momentum. That's the semi-truck, right? It's going to be a whole lot more. It's going to have more momentum and it's just going to completely take me out. Whereas that car is going to have less momentum because it has less mass. Now, the calculation to calculate how much momentum an object has is a simple equation. P stands for momentum. Why that is P, I have no earthly idea, but somebody thought that was a great idea once upon a time. Notice that the unit for momentum is kilogram meters per second. Okay, kilogram meter per second. And we can calculate momentum if we multiply the mass times the velocity of an object. Okay, so as the momentum increases, as the mass increases, the momentum is going to increase. Same with velocity. As the velocity increases, the momentum increases. Again, that explains my baseball, right? That baseball that is going 100 meters per second is going to be very, very hard to change the course of its motion because it's going so very fast. So again, pause the video, pause the recording as you need to complete questions 12 and 13. Now, here we're going to calculate the momentum. And this time we're going to calculate the momentum of a bowling ball that has a mass of 5 kilograms. Again, momentum, P, is what we're trying to find. And the velocity is a positive 3 meters per second, meaning that that bowling ball is rolling forward, right? So kilogram is my mass, 3 meters per second is the velocity, and we are solving for momentum. Okay, so here is my formula, and I'm just going to plug this in. 5 kilograms times 3 meters per second. 5 times 3, I get 15 kilogram meters per second. Okay, and that is the answer for question number 14. Easy peasy, lemon squeezy. Go ahead and pause the video as you need to. Now, question the next question, is that 13? I think it might be 13, is a little bit different. Notice we are still calculating for momentum, right? Our mass is still 5 kilometers, but this time it's a rock and the velocity is negative. Notice that it's negative because it's falling from a cliff, right? So that negative velocity means that it is falling downward, right? So again, we've got 5 kilograms. We have velocity of -3, and the momentum is a negative momentum, a -15. And again, all that means is that in order to change this momentum, right? The momentum is being pulled down, right? So this motion is going down. And so we would have to change that direction to change its motion. Okay. So now we've got another question. This time we've got a soccer ball. Okay. Again, we are solving for momentum, but the mass is smaller. Look, it's only 0.4 kilograms, right? But the velocity is the same as the bowling ball, okay? So this time I have 0.4 kilograms times the velocity of 3 meters per second. So this soccer ball is moving forward just like that bowling ball did. But when I multiply this, notice what happens. My momentum is much smaller than it was with this bowling ball. With the bowling ball, it was 15 kilogram meters per second. But now with the soccer ball, it's only 1.2 kilogram meter per second. Why is that? What just happened? Well, I know that that bowling ball has a higher momentum because it's got a bigger mass, right? So the bowling ball has more momentum because it is heavier. And that is the answer for question number 17. Okay, so what we've done today is we talked about the difference between mass and weight. We talked about free fall and how to calculate the velocity of an object in free fall. And then we shifted just a bit and we talked about momentum and how mass and velocity affect momentum. I hope you have a lovely, lovely day.